Hello and welcome everyone. In this common algorithms learning, previously we have looked at Dijkstra's algorithm, which is helpful in finding a shortest path between two vertices, a source and a destination vertex in a graph. While in this video we are going to be understanding Prim's algorithm, right? So Prim's algorithm is one such similar algorithm to Dijkstra's. Instead of having to calculate shortest path, we are looking for minimum spanning trees. A minimum spanning tree in a graph uh, is one where all of the there would be all of the vertices, and there would be minimum number of edges such that the weight of the subtree from the parent graph is minimum, right? So there should be all uh, vertices with minimum possible edges. So it's like we can take an example of MST as having to establish uh, network cables to all the home with shortest path or shortest weight, right? So this is slightly different from uh, the shortest path algorithm of text. Let's look at the code. Uh, Before even going into code, let's start with a motivational quote, and then let's start understanding the code or the implementation for Prim's algorithm. Anticipated problems exist in your head, real problems exist in the world. Spending too much time solving imaginary scenarios lead to wasted effort on things that may never happen. Life has a way of surprising you with challenges you never predicted. By focusing on actual practical problems, the ones right in front of you, you build real skills, deliver real value, and stay adaptable. The best coder isn't the one who predicts everything, but the one who solves what truly matters when it truly matters. Right? Instead of having to imagine a problem, it is more important to get into the real world and having to solve a real world problem, which gives us a lot more challenges and build real value, and always adaptable to market changes and market needs. So that's one thing that I wanted to communicate in this motivational quote, right? So let's start understanding Prim's algorithm. So let's take an example of a graph which has a path, let's say 0 connected to 1, 2 and 4, and 0 also connected to 3. So let's say this as 6 and 8. This is an undirected weighted graph. Okay, so consider this as a graph, and we are required to calculate uh, the MST, or the minimum spanning tree. Currently, the weight of this specific graph is 6, 8, 2, 3, 7, and 15, which comes down to 15, 20, 26. Current weight 20. Okay, so 10, 20, 25. Okay, so these two add up to 10, 20, 25, 31. So let's say when we convert it to MST, a minimum spanning tree, this same graph would look like uh, 0 connecting to 3, and the MST should have all vertices and minimum weight and least edges. So MST is minimum spanning tree. Okay, so 5 and 3, 2 and 6. So the current weight of this is 16, and the number of edges, as you see, it would be 1, 2, 3, 4, 4. Uh, while we have, it is also equivalent to vertex minus 1, right? So this is, so here we had edges 1, 2, 3, 4, 5, 6, 6 edges, and vertex is equals to 5 vertex. Whereas here we are having minimum edges and same number of vertices, right? So that's a minimum spanning tree. The way that Prim's algorithm works is okay. Now let's understand how the algorithm for solving Prim's or MST with Prim's algorithm works, right? So let me just start off with a new page. Maybe I will also copy this piece of graph in a new page. Okay, so here we have this graph. So few things that Prim's algorithm requires are a priority queue, key array with v vertex, and a parent array with same v number of vertex, and a visited array with v number of vertex. So these are the set of things that would be required in a Prim's algorithm. So the way that the algorithm works is initially all of these key would be of a weight. Priority queue would take in uh, vertex and a weight. So it will obviously be sorted with the value of weight. So we can expect um, the topmost of the priority queue to be the minimum value. So we run a while loop with initially starting out from 0 comma 0, and we start off with a zeroth node, and we explore loop pq is not empty, and we check if uh, this specific node, the zeroth vertex, is unvisited, and we dequeue pq.dequeue to take out values of uh, vertex and weight, right? So we take the vertex and we mark it as visited true, and we run a for loop with all its neighbors, and we constantly keep uh, pushing items. We constantly keep pushing uh, the values of the unvisited edges to the priority queue with also updating the same in the weight, which would track the minimal possible MST weight of the specified graph, right? So let's take one example. So here, let's say we have zeroth node, which is connected to 6, 2, and 1. So we have this priority queue which starts from 0 comma 0, and it in the first iteration, in the iteration 1, it takes up something like DQs, and it takes up, first thing is uh, 3 comma 6, 3 comma 6, and 2 comma 8. Priority queue will arrange everything in a ascending order, in a specific order that would be easy to pop the topmost element, giving the minimal value. So, and 1 to 2. So this would be the minimal value, which in iteration 2 we would pick this value. So far we have got that 0 is connecting to 1, right? And we also mark a 0th node as a visited one. At the same time, in iteration 2 we pick this specific node, and we would not be looking at the visited node, which is 0th vertex. So we check the edges connecting between 1 and 2, 1 and 4. So these two we mark them. So we again mark them this way. So we would be having 2 comma 8, 3 comma 6, and also we would be having this one, which is of slightly higher, 4 commas 5, 4 comma 5, and also 1 to 2, which is 2 comma 3. So this would be the value, right? So now we know that this is the minimal value, so we establish this node. So we know that this is the one. So now we, in the iteration 3, we pick this value and we explore all the connected edges between the node 2. Say we already have 2 comma 8, 3 comma 6, 4 comma 5, and 2 comma 3 we would be exploring the node 2. So, and also our MST so far is 0, 1, and 2. Is 0th node, 1th node, and 2, 3, and 2, right? So this is our current MST, and now we have DQ 2 comma 3. So we are going to explore the vertex 2, which is connected to 0. We, since 0 is a vertex which is already visited, we would not be exploring the vertex. Uh, Here we have 1 comma 2, and here we have 2 comma 3. Here we are exploring 0 comma 0, right? So these are the nodes. So all of these nodes will also be marked as visited at each iteration, considering the minimal value. So with the node 2, we also have uh, since 1 and 0 are already marked visited with iteration 1 and 2, we would only need to consider this specific edge, which is 2 to 3, 2 to 4, sorry, which is of value 7, right? And we also we need to 2 to 7. So let's put this here and let's consider the minimal value out of these, right? So the minimal value here is this one, which is 4 to 5, and the node that is unvisited here is this one. So that's the way that this priority queue operates, 4 to 5. And 4 to 5 is an edge connecting between the node. So this is a edge that we should be considering instead of this one, because this has a priority value 5, right? So that's the way that this goes. And next thing is we dequeue this specific value in iteration 4, 4 comma 5, and we also mark this node as visited, and we have these set of nodes 4 and 7. Since 4 is already visited, we can ignore this. 3 is already visited. 3 is not visited, so we explore the path 3. So we get 3 comma 6 and 2 comma 8. So this is the topmost one, and we explore this one. So with this one, we can also say 2 comma 8 is already a maximum, and we ignore it because 2 is already a visited value. So hope you found understood this algorithm. With this understanding, we will quickly jump into the JS bin and show the MST solution or MST algorithm, that MST result that Prim's algorithm gives in JS bin, right? So this is the whole step-by-step walkthrough of Prim's algorithm, right? So here we have a priority queue, and this gets sorted every time we enqueue an element, right? So, and this was the whole initial set of data or data structures that we need. One is a key which tracks all the weight, and a parent array which uh, gets updated here with the minimal or the MST path. And another thing is we have a visited array initially marking with an value false to all vertices, and a priority queue which starts at vertex 0, and we start with this while loop iterating through all the edges, and we mark each edge at each iteration true, as we saw in our drawing board, and we explore all the other edges with the specific vertex with a specific vertex, and we enqueue them, and this priority queue has it sorted in a minimal value, which when dequeued we explore the next minimal edge, and that way we continue here, right? So this was the same value that we saw. So 0 to 1, 1 to 2, 0 to 3, 1 to 4, right? So switching back to drawing board, 0 to 1, 0 to 1, 0 to 3, 1 to 2, 1 to 4, right? So that's the whole result that we are seeing here. Okay, so with that being said, let's quickly look at the time space complexity that we have for this algorithm. I have even added a short description on the same. So we iterate through all the vertices and edges. So enqueuing into a priority queue takes a operation of log v, and that's the reason we have time complexity of v plus e log v and space complexity of v plus e, where there is adjacency list and priority queue, right? So yeah, this was about Prim's algorithm. Hope you found this video helpful. Please do like and subscribe to my channel. Please do post any comments or any doubts or any clarifying questions that you want me to address. Until then, please do like and subscribe to my channel. Thank you.